is a slender rod with mass m, length L. It's got some external force acting on it at location B. And then there's an external moment acting about the center of mass on the system. It's drawn at the unstretched position, and we are assuming that the springs only act in the vertical direction. And then again, I didn't write it down, but we want to find the equation of motion governing this system. So we start off with defining our Cartesian coordinate system. We put that at the center of mass for the undeformed configuration as shown here. We then went and drew a second version of this where the system is deformed, and then defined position vectors from there. We defined several relative position vectors as well that we'll use for calculating moments. We then went and determined the acceleration of the center of mass and the moment of inertia. We're dealing with the rigid bodies moving in a plane here, so the angular velocity and angular acceleration are always as defined and shown here. We then went and did a free body diagram, and then we started applying Newton's laws, which are also Euler's laws. We started off with just the translational form, and now we're going to go and do the rotational form to compute the moments acting about the center of mass. Okay, so where are we? So we found our equation of motion for y of t. We're now going to take some of the moments about the center of mass. And if the system were pinned somewhere, you would take some of the moments about the pinned position rather than center of mass. But this is going to be equal to the moment of inertia. In fact, I have it written up here. It's equal to the moment of inertia times alpha. Here we're going to actually go and compute the moments. Just as a reminder, these are equal to, well, it's going to be the sum of all the position vectors crossed with the corresponding forces. We'll start with the spring force at position A. In this case, this is going to be our position vector for r/CA up here. It's minus a cosine theta. Cosine theta in the I direction, minus a sine theta j. That then crossed with our spring force, which is minus k times y minus a sine theta. All that in the j direction. Plus, then we're going to do all the forces that act at B. We don't need to include gravity because gravity is acting at the center of mass, so that there's no, it doesn't generate any moment. For position B, a relative position vector is B times cosine theta I plus B sine theta j. That's going to be crossed with all of the forces acting at B, f of t minus k times y plus b sine theta, all of that in the j direction. And then also lastly, plus the moment, m of t, and that acts in the k hat direction. Okay, so if we go and we compute those moments, we will get everything's going to be in the k hat direction, and we're going to end up with Ka cosine theta y minus a sine theta plus f of t times b cosine theta minus kb cosine theta times y plus b sine theta plus that external moment, all of that in the k hat direction, and this is equal to IC times theta double dot in our k hat direction. Okay, and then we can go and substitute in and rearrange, and we'll get ml, or 1/12 ml squared, that's the moment of inertia, times theta double dot, plus k times a cosine theta. Actually, hold on a second. Okay, I leave out a minus sign. Oh no. Yeah, Ka times cosine theta, and then a sine theta minus y. So I brought this term over to the other side, and then I absorbed the minus sign and switch the order. And then we'll get plus kb cosine theta y plus b sine theta, and then this is equal to m of t plus f of t times b cosine theta.
The first part of the Goldberg equation, why are the parentheses being multiplied by x?
By x. You mean you're talking about right here?
Yeah.
Yeah, that's a cross product. Yeah, I can see why you would think that. So, yeah, that's our cross product. Yeah, so I just ran out of space. So we're taking the cross product between the relative position vector and the forces acting at that position. Yeah. And then this is our equation of motion, and we get for this two equations of motion, one governing y of t and one governing theta of t. And I left this term with the f of t times the cosine of theta on the right-hand side, simply because if you consider small angles, then this cosine will go to 1, and then you'll get the forcing on the right-hand side. That's why I left it there. If you don't have small angles, then in fact this would come over here, and it turns out it's what we would call a parametric resonance system, which you don't need to worry about. Our goal is to either find equations of motion or apply Newton's second law or Euler's law to understand how forces affect accelerations or vice versa. And in later classes, you will learn how to solve these equations. Probably, if you haven't done DiffyQ, you'll learn it in DiffyQ, and then you'll relearn it again when we take like AE 3530 and other classes as well. And if you want to study parametric resonance, you've got to take a nonlinear dynamics class. All right. So I have here the moments of inertia are covered in Appendix C of the textbook. I believe that is true. Somebody will need to check for that for me. I believe I did update it. I used to use a different textbook to teach this class when I taught at a different university. And I'm pretty sure I updated this, but I'm not 100% certain. Because I made these notes like 3 weeks ago. Okay, any questions on what we did here? Okay. So yeah, when we deal with moments of inertia in plane motion, there's always 3 moments of inertia, but we only care about one of them in this. When we go to 3D, we will kind of see how it kind of blows up, and you'll have to deal with all 3 of them. Okay, we're going to briefly talk about parallel axis theorem. There's really not a lot to say. We're not going to derive it or anything. But simply, if a rigid body is rotating out a point that's not the center of mass, such as what I've drawn here, this little bar that's pinned at a distance d away from the center of mass, then your moment of inertia is just going to become modified. It's going to be equal to the moment of inertia about the center of mass plus the mass times the distance from the center of mass to the pin position squared. And so this will pop up in homework. It's going to pop up in the worksheet today, and it may pop up in exams as well. It's a very simple formula, which also means that it's very easy to forget. So make sure you note it. Okay. Yeah, there's a resonance of those blinds occurring. So there are like standard shapes, and I'll probably just give it, in all honesty. When we get to 3D, we may start thinking about how do we calculate these, because in 3D it's not as easy, I would just say. I don't know. Either, there are some very simple shapes like the moment of inertia of a rod is just 112 ml squared over 12. If it's anything complicated, I'll just give it to you. And I may just say it's like I, or it's J or something. And then you don't know what it actually is, and you just leave it as that. Any other questions? Okay. We're going to go on to rolling motion then, finally. So rolling motion is an important type of plane motion. It can only occur when friction is present, so there has to be friction in your system. If there's no friction, then you can only get sliding motion, or what we'll call slip. So things can only just slide along the surface. They can't actually roll. There are three cases of rolling that are important. First is just rolling, no sliding. This is often called rolling without slip or with no slip. The second then is rolling with sliding and pending. And the difference between these two cases is that you will know something about the friction force for the second case, which we'll cover when we get to it. For the first case, you won't know what the friction force is. The friction force will be whatever it needs to be. And then the third case is not a rolling case, but where you have a disc or whatever rotating and sliding. Or I guess you could say this is rolling with slip. Okay, we're going to go through all three cases. Case 1 is the most interesting, with case 3 being the second most interesting, and case 2 is really like a subcategory of case 1, where you know a little bit more about what's going on. Okay, so when a disk rolls without slip, there's going to be no relative motion between the contact point. I don't know why this is said twice. Between the contact point on the disk and the ground. And what that implies is that that the contact point is the instantaneous center of rotation. In this case, friction force is comparable to static friction acting on a block at rest, but we don't actually know what that is. we can write here that our friction force is going to be less than mu s times whatever our normal force is, and we don't actually know what that is. We can certainly compute a normal force acting on a disk. I mean, I've drawn a free body diagram on a disk to the left here, where it's being pushed by some force P. We got gravity pulling it down. You got some normal force pushing back up, and then you got friction. So you can certainly calculate this normal force. The thing is that the friction acting on this disk is less than mu Sn. And then as a result of this, the acceleration of the center of mass, or the central point of that disk, is going to be equal to r times alpha, so r times the angular acceleration, and then similarly the velocity is r times the angular velocity, and then the displacement of the center is equal to r times theta. And that's because this disk is rotating, it's rotating about this contact point. So a great real world example that you can go and like see is to go to a bowling lane and watch bowling balls as they spin versus when they're sliding and spinning at the same time. You can see, it's very easy to see the difference of how if a ball is rolling very slowly but translating very fast, you can very easily see a difference between, you know, the rotation plus the slip versus when it's just perfectly rolling. Okay, yeah, in equation 6 here, this is true for the center of mass at the center of the disk. If the center of mass is somewhere else, then it's the distance from the contact point to the center of mass. Okay. So for case 2, this is when sliding is just impending or about to happen. This is where the friction force is going to reach its maximum value. And so this is a case where you'll know that this friction force is exactly equal to, in this case, it's going to be equal to the kinetic friction, oh, I'm sorry, it's still static friction, mu s times n. And then acceleration terms are still the same, velocity is still the same, and the displacement is also r times theta. And again, this is for the center of mass at the center. And the contact point is still the instantaneous center of rotation. Okay, so in case 3, this is where our disk is going to both rotate and slide. This is generally called rolling with slip. And as a result, there ends up being relative motion between the ground and the contact point on the disk. So basically that contact point is also moving or translating. And this is just comparable to a sliding block. Okay, so in this case, our friction force is just going to be equal to the kinetic friction, or mu k n. And then in this case, xc, vc, and ac, these are all independent. So independent of theta, omega, and alpha. So rolling is really a constraint that applies to the system that relates the translation to the rotation of the system. It's a kinematic constraint. And when you have rolling with slip, they're independent of each other, and you end up with 2 equations. of motion, one for your theta, one for your ecstasy, or one for the rotation, one for the translation. As a result of this, we don't necessarily know where the center of where the instantaneous center of rotation is. Yeah, I don't know what, there's a typo there. Okay, so what do you do if you don't know if a disk is rolling with slip or without slip? The general strategy is to assume that it's rolling without slip, and then go and solve and find your friction force. And if the friction force is greater than static friction, the static friction force, then you know the disk is rolling. It must be rolling with slip. If it's less than or equal to that static friction force, then you know that it's okay, that it is rolling without slip. If you find that it's larger than this maximum static friction force, then you need to go back and restart the problem with the assumption, well, not assumption, now you know, but restart it with using equations for rolling with slip. Okay, any questions here? So generally in like an exam type setting, now I'm not saying this is what I'm going to do because I don't remember what I did when I made the exam earlier. I'm not even sure what problem's on it anymore, but I'll probably remake it anyway. Generally, you're told that the disk is rolling without slip or rolling with slip. That's my personal experience having done this for several, having been a student and have taken exams on this stuff. You're generally told whether it's rolling without slip. That's probably what I would do as well, because the problems can be long, and having to restart after going through all of that analysis ends up just costing a ton of time. Okay, any questions before we go on to an example? Okay, and then we're going to go take a look at example 2 here. We are considering a disk that's connected to a hanging mass through a frictionless but not massless pulley. So this is one of the first key differences here, is now we have a pulley that has mass, and we'll need to account for its dynamics. The disk here rolls without slip. So again, we've been told that it rolls without slip, and we're including gravity here, and we're asked to determine the governing equations of motion here. Okay, so generally you would assume that the motion of this block y of t is equal to the displacement x of t. However, because the pulley has mass and therefore has inertia, and if it ends up being that these two may not necessarily be equal, and it's something that you need to analyze and find out. That's what we're going to end up doing. Let me check here. Yeah, what we'll end up having to realize is that the rotation of this pulley will be related to the displacement x of t and the displacement y of t through a kinematic constraint. Okay, but we will have to account for the inertia of that pulley. Okay, we're going to start. We're going to put our solution here. Oh, I got it over there. Okay, we're going to start with just a standard Cartesian. I put it at the pulley. At the center of the pulley. What else are we told here? So the disk has a radius of 3r. The pulley has a radius of r. The disk has a mass of m1. Pulley has a mass of m3, and then that block has a mass of m2. For the pulley, we're not told what we're told that it has a moment of inertia I. So this is what I mean when I'd say I tell you what it is. I tell you it's just I. Let me see what it is. This disk is being pushed by a force acting at the center, and we're going to measure its rotation using theta of t, the displacement of that top point with x of t, rotation of the pulley using phi of t, and then the vertical displacement of that mass, m2, using y of t. Okay, so I've gone and drawn the position vectors as shown here. R1 goes to the center of the disk, or the center of mass. If I don't tell you that the center of mass is somewhere weird, then you just assume that it's at the center of the disk, or the center of whatever object you're considering. Okay. So for R1 here, we're going to get that this is going to be equal to, well, x of t and this x of t is drawn at the center of mass here, not at this, not at the top. That's my mistake when I said that. It's drawn from the center of mass. So this is going to be x of t minus at distance b in the I direction, minus 2r in the j direction, r2 here is going to be equal to, we're going to move over r in the I direction, minus h plus y in the j direction. And then here x, since we're rolling without slip, this is equal to 3r theta. All right, we're going to go and compute velocity and acceleration vectors, and then we'll stop for today. All right, so for velocity vector for R1 dot, we're going to get here x dot in the I direction. That will be equal to 3r theta dot in the I direction. R1 double dot is going to be equal to then x double dot I equal to 3r theta double dot I. R2 dot be equal to minus y dot j. R2 double dot equal to minus y double dot j. Then for our pulley, the angular velocity is going to be equal to minus phi dot k hat. Alpha p for the pulley is going to be minus phi double dot k hat. Okay, so on Monday we'll go through free body diagrams for this problem. Then we'll go apply Newton's second law or Euler's law, and we'll go and solve for the equation of motion. Okay.